Okay, welcome back and good morning wherever you are, or good afternoon again. So, we discussed in the last class the review little bit of phase transition, then I talked about two things I left out and not in great detail, but students should know about them, is the sol-gel transition, which is a very common chemical industrial phenomena, and percolation, which is again very common in electrical engineering, and these things. Percolation is very common in natural, as I said, in sand bed and many other places. Flow of water is dictated by percolation. And then we talked about that the Landau, little bit revised Landau theory, the Landau's great free energy landscape picture of phenomena. And then we talked about that first order phase transition is where you have a metastability as given by hysteresis, or given by the fact that we all say that water freezes into ice at 0 degree centigrade or go below 0 degree centigrade, but that does not quite happen. If you have a very pure water, you can make it into droplets so that no impurities there, then that remains in the liquid water till minus 40 degree centigrade. Mercury and gallium, you can supercool, we call them supercool to about minus, below their melting, their freezing point, 50 degree centigrade, 60 degree centigrade. Even in upstairs in clouds, the water, the temperature has to go down before the really cloud, the droplets form. And this is what is already in Van der Waals theory, in a kind of Van der Waals loop. And we know in metastability in magnetic systems, you switch the field in the other direction, but nothing happens. The spin still point, magnetic moment still point in the old direction. You have to turn your field quite a bit before they turn around. So, metastability means that system is trapped in a minima, free energy minima, and that can be explained very easily from Landau's picture, that there. In a first order phase transition, the old minima remains. So, even though new minima, deeper minimum has appeared, the system does not know how to go around. It does not know even that, probably knows that there is a new way of doing it, but it does not know. But what happened? System always undergoing fluctuations, and these fluctuations is a way of exploring the thing. And as we discussed in the thermodynamics, that these fluctuations must be positive for a system to be stable. That is why specific heat stability, specific heat greater than 0 is a condition of thermodynamic stability. Isothermal compressibility positive is a condition of mechanical stability. Essentially, these fluctuations are, we consider in a stable system, the fluctuations around a harmonic surface. So, free energy can be, that is why how does it come? Because if it is a probability of a fluctuation of energy, that is Gaussian, e to the power minus delta E square, and what you have in the denominator of delta E square? You have the specific heat. So, if I talk of a fluctuation delta E, then that goes as normalization constant e to the power minus delta E square by Cv. So, if I have a harmonic thing, then this Cv is fluctuating, then what is the probability of fluctuation delta x? If this is x, then it is again e to the power minus omega square delta x square. So, omega square, now you compare the two, the frequency is Cv, 1 over Cv. So, omega square is 1 over Cv. So, this a stable system is bound in a harmonic surface. So, right now what we are having then? We are having this kind of situation. This is harmonic, but this barrier is large, the barrier is macroscopic. So, barrier is macroscopic, very important. So, how does the system go then from here to here? This is the question. In second order phase transition, it does not arise. Second order phase transition does not have metastability. It has just large scale giant fluctuations appear with the divergence of compressibility and specific heat, and you suddenly get these the system split into two, okay, ordered and disordered. Like in magnetic transition, you have ordered state and disordered state, and a system choose between one of the two. System choose between, sorry, system upspin and downspin, and that's a beautiful phenomena called spontaneous symmetry breaking, but we are not going to go into that right now. We are going to do it first order phase transition. So, this is the first order phase transition. We will do second order more detail later, but something extremely important to a physical chemist and to nanomaterial synthesis of more importance of late now to material scientist and to physical chemist, or in the department I am in solid state and structural chemistry, or the next my department chemical engineering, is very, very important that one understands the nucleation phenomena. And this is something I can tell you a small story. Once I was visiting Japan and I gave talk, and it was the first time, and I was not comfortable with Japanese food, and I was very hungry after my talk lecture. So, there was an Indian student who was my ex-student. I was not my own PhD student, but a student, another faculty member. He was very eager, sent me many mails, he wants to see me. So, I remember it because after the talk I was very tired, and he took me to his, I did a long talk. In Japan sometimes you give 2 hours lecture. I went to, at 6 o'clock, I went to his office, and I told him, first before you talk you give me some food. So, he gave me a couple of banana, but then he was so, told me, sir, I wanted to see you because you saved my life. I said, how? Bolo, you taught that course on nucleation and spinol decomposition, and here when I came they were doing something on a surface which was actually nucleation, and they didn't know anything about it. And so, but I knew from your class, so I could explain the experimental phenomena to them, the formation of islands, and then and they were and percolation and all these things, and they were extremely happy. And the first paper that I could read write within a short time. In Japan it take a long time sometimes to write a paper, especially by foreign students. But this guy was so. Then I realized that this guy was doing a surface scientist. So, all the critical phenomena, critical exponent, renormalization group that you teach them is not useful to bulk majority of material scientists and to physical chemists or organic chemists. But nucleation is very important, because nucleation is more important than critical phenomena to this group of people, because they face that all the time. A physical chemist, this is an experimental physical chemist. So that I always preempt, I before critical phenomena and any other things, I teach nucleation, and I want students to learn nucleation. It's a beautiful phenomena. Okay. So, now how does nucleation then what happens actually in this system when you have this phase, my old phase. In that old phase, the way it goes over to new phase is that a small embryo forms. So, this embryo is a nuclei, that nucleus of the new phase, and that tries to grow. So, in this landscape, this is somewhere here. So, this guy tries to grow by fluctuation, is a spontaneous fluctuation, and it goes, then it comes down again, then again goes, finally it goes here and it goes over, and then there is an explosive growth. So, the process of the phenomena of an embryo growing into a metastable phase is nucleation. So, nucleation is the process, let me write down. Where by an embryo of the old phase undergoes growth by activation, and this is spontaneous. It has activation energy, and we will now calculate the activation energy. So, this is the nucleation. So when a first order phase transition happens, not by any kind of big large scale fluctuation, but the small fluctuation that goes. So, the system is destroyed from within, from inside the system is destroyed, and new phase comes up. That is how ice melts, that is how water goes into ice or water droplets form. All the first order phase transitions, or if you have a magnetic transition, but in the presence of a magnetic field, then this some localized spins get ordered from the disordered system, and if you have field on the upside, then up spins will get clustered together and they form a nucleus or an embryo, and then that embryo will melt and go, but finally it will grow. They are growing in many places, but one of them will grow and reach to this critical size, and then it goes over to the other phase. So, that is the phenomena I will describe now in a little bit more detail. Okay. So, we will now do the following thing, that we will do nucleation. I described already thermodynamics from nucleation and the Becker-Doring theory. Then we will do some things, very nice things, which is Zeldovich treatment of the correction of Becker-Doring. By the way, the Becker-Doring is an extremely important thing. This is the thing which is described in many cases. Physical chemists might know. Lindemann thing, then enzyme kinetics, Michaelis-Menten, and all these things, they are all very similar things. They are connected to each other. So someday, if I can get time, I will talk about that. Okay. So then classical prediction, limitations, and all these things we will do. So let us start with then the nucleation. Okay. Is a phenomenon observing in the large kinetics and phase transitions, and it is from within. So there it must proceed via nucleation, because macroscopic free energy barrier, it cannot, this I already told, the barrier is macroscopic, it cannot go otherwise. So it must form from inside. So nucleated, so new phase has to be nucleated within the old phase, that I said, and however, this process itself has a barrier, and that is a nuclear barrier, and that is a beautiful physics, and that is called nucleation barrier, and that is the one we will now consider. Okay. And then an example, as I already said, that water should freeze at 0 degree centigrade, does not. It is can be super cooled to great much below minus 40 degree centigrade. Water remains water. Pure water does not freeze at 0 degree centigrade. That because the embryo needs sufficient driving force to grow. It does not grow. Okay. And this is the existence of metastability is due to this is a beautiful sentence actually. This is all taken from our book, that the existence of metastability due to the presence of barrier forced by nucleation. Now, while pure water does not freeze below 40 degree minus 40 degree centigrade, helium and gallium and mercury does not below minus, they go 50-60 degree centigrade below, they are freezing. However, in refrigerator ice forms, minus 5 degree centigrade or minus 3 degree centigrade, 10 degree centigrade. The reason is that there are surfaces and there are a lot of impurity. So that is called heterogeneous nucleation. Heterogeneous nucleation does not face that barrier. And there is the way you do the heterogeneous nucleation, of course, you have to do homogeneous nucleation first, then you include the surfaces and show that how heterogeneous nucleation takes place. Okay. So this is a completely smooth way, and one interesting thing is that you are having a very and you might have done in physical chemistry experiments that you have supercooled it and you have the container below 0 degree centigrade. Now you scratch it with and many of us have seen that, or any liquid, you scratch it with a glass rod, and you can see crystallites appearing. So, the heterogeneous nucleation, and this is because this is one of the telling and great example of the role of surface tension. And surface tension is something we want to study in this lecture later, but right now we will define surface tension as the energy required to create a surface. So, if I have to create a surface of ice in water, that is a different surface that requires extra energy, that is energy surface tension. Quantitatively is defined as the energy required to create an unit area that you have read in your high school even, that surface tension, but that same high surface tension plays an extremely important role. Now how do you go to do the theory? And we are now going to towards that development of the theory. Okay. So, the basic idea then that we have an embryo growing in this old phase, embryo of the new phase is trying to grow, and you have to find out what is the energy. Okay. When I grow something, then it gains energy because the free energy landscape is like that. So, this is the new phase, the embryo phase. So, when it is here, it gets free energy, it gets considerable of free energy, say the free energy per unit volume I define as delta GV. So, it gains that energy. However, it creates this surface and it has to pay for the surface. So, total delta G is then sum of bulk energy which is gained, this is minus negative, but then surface energy which is it has to pay. So, these things, and some of you might already beginning to see what is that. So, this is the metastable gas, and in this case this is metastability in temperature versus density, and this is the critical point. Okay. Now, so as we again and again saying, if gas going to liquid, then this is the coexistence, but in order nucleation to take place, it must go down, and I am now going to tell you why is that. Okay. So, basic equation is this is the equation. Okay. The basic equation is that if I want to create a nucleus of radius r in a old phase, then my volume is 4 pi by 3 by r cube, this is 4 pi by 3 by r cube, and then delta GV these are great things, and delta GV is the difference, this is the delta GV. So, this is the I gain, so this is negative in front, I gain this much, I gain. However, I have to pay energy. So, how much is the surface? We know surface is 4 pi r square, and gamma is the energy per unit area. So, 4 pi. So, this is the total amount of. So, in order to create a fluctuation of size r, this is the energy that I have to pay. This is the total energy cost, energy gain and energy loss. Now, what do I do? Okay, I go here and I ask for a new page. Okay, so let me now see delta GR. Now, one is energy gain and this, and how do they look? Let us look at this. These are cube and these are square. So, if I plot this delta GR against R, then this thing is negative, this R cube, this thing is positive. Okay. Now, surface tension is actually pretty large. So, what happens? This part wins in the beginning. So, that is why you go up the hill and come down. But if by some fluctuation it becomes large, then it starts getting the advantage that this is larger because these are cube. Okay. So, then what happens as a combination of these two, a maximum appears, and this maximum is very important thing in the language. These are star critical radius, this is the critical barrier. So, in the folklore of phase transition, this is a very important diagram that is telling you how nucleation takes place. This is very important for nanomaterial synthesis and every case. This one diagram called Baker-Doring diagram, that when I write free energy of creation, embryo of size R, then this has this structure. Now, how do, so again combination of two factors, one is negative, rapidly becoming negative, other is positive, and then you get that. Then how do I do that? Then next thing, of course, and this is the critical radius R star. I have to find the expression for R star now, and critical barrier. I have to find an expression of critical barrier. Okay, let me do that. How do I do that now? We have done it many times in this class already. We do d dr delta gr equal to 0. Okay, and what do I do now? I do this. So I writing little big, I should write little small. So when I do that, I get minus 3 cancels this 3, and I get 4. I get minus 4 pi r square delta GV, and I get that plus 8 pi r gamma equal to 0, right? Now, one of them r is equal to 0 is the solution, part of the reason because this is the minimum. So, r equal to 0 is the solution, that is not the solution you want. So, we then divide by r. So, this goes out and these become r. Okay. Now, these are now become my r star. I now the other second solution is r star, and that is now given by r star by 2 gamma by delta GV. So, these r star is a beautiful expression. So, this is the radius expression of the critical radius. Now, what I want to do? I want to put this value of r star into this. So, now I want to do find this barrier. So, now I put it made it r star, okay, and I put r star 2 gamma by delta GVQ here. I'll use the same equation, excuse me, but that will work out beautifully. So, 2 gamma cube, and now I'll put square. Okay. So, now you get 8 and 32 by 3, here you get 16 by 3, and delta GV, this delta GV cancels one of the delta GV here, and you get gamma cube by delta GV square back in the. So, now I get the following expression. So, these are the two very important expressions. This theory of nucleation is called Baker-Doring. Let me tell you, this also the theory was used in nuclear fission and many across the condensed matter physics and chemistry. It's amazingly important and beautiful thing. So, basically what we have done, considered a combination of surface term and the bulk term, and I just wrote down a very simple expression. Surface tension is known, so is delta GV is known because I can calculate the free energy of the old and the new phase. I can come from the old phase and I can come from the new phase, and I can calculate the free energy things by standard free energy calculations. I can do that by integrating over specific heat. That is the way we set up the problems, that I give you enthalpy, I give you specific heat, and you calculate the free energy, that can be done. So, free energy of these phases are fairly well known, and there are many fittings also available to these things. So, we know delta GV, we know the surface tension, and there are certain approximations, and we will talk about that. But since this is a StatMech course for aim to for beginners essentially, we will probably minimize the criticism of a theory of the scale, and we will discuss, of course. Now, but I want you to appreciate the generality of the concepts that are involved. It is a very common generality, and at the end of the day, we come out with certain beautiful expressions, and which are very widely used, very widely used. So, when you say, or you hear the term nucleation is thermodynamically controlled or kinetically controlled, all these kind of a thing, then many times what is talking about nucleation, that if it follows the low barrier pathway, even though the state is thermodynamically more stable, that we'll do now. Another very beautiful thing we'll do, just amazing, the important things, not usually covered in textbooks, but we'll do, is the Ostwald step rule, and extremely important in present scenario of solid state synthesis. So, so those with thermodynamic control, kinetic control, all these things are essentially we are talking of nucleation, and so these are the two equations I just derived. So this is the size of the critical nucleus, and this is the barrier of the, very beautiful equation, 2 gamma of delta GV. We all almost know this by memory. Okay. So now, how do I do that? How do I do now? So I have a situation like that, and this is my free energy barrier, delta G star, my R star. Now you ask me, what is the rate? How do I calculate the rate of nucleation, Rn? How do I calculate that? Ask a chemist that I have a barrier, I have to go over the barrier. A chemist will immediately say, I know, there is a activation barrier. I know what is the activation barrier. It is delta G star by kBT. I know that. Okay. Well and good. Then what is the P factor? So this part chemist will do. Then the chemist will scratch his head. I am used to do transition state theory. If I have a barrier, I have a situation like that, I write rate K equal to K Boltzmann factor by Boltzmann factor times temperature by Planck constant e to the power minus delta E star by E star. E star by kBT. I know that this has been taught to me from school days, that this is the rate of barrier crossing. Can I do it here? Okay. So this is the Boltzmann factor, the weight of the probability that the particle is at top, that gives you this term. That cannot go wrong. This has to be correct. Then, but how do I get this term? I will do a chemical kinetics a little bit somewhere down towards the end of our road, because we take a bond and we say, okay, the bond breaks, and the bond is a frequency, nu and H nu, and that is about thermal energy kBT, and then say okay, nu is the frequency of breaking is kBT by H. That is how we do it. Then how do I do it here? How do I do it here? Well, we do in a way not too different. We will do in a way which is essentially follows this logic, but in the process we do something really extremely beautiful, which is very much like chemical kinetics, and it turns out what we do is a chemical kinetic, is a form of chemical kinetics. And again, the guy who did it is a nuclear physicist, very famous nuclear physicist named Zeldovich. And what he did here was essentially in the atomic bomb, that same thing used in chain reaction, and it will do exactly chain reaction and in fission, and this beautiful stuff. So we'll stop it here, and in the next class we'll be doing the Zeldovich correction and finish the nucleation theory.